All right. Good afternoon, everyone. So at this point in the course, everyone has written all three tests now. So the tests are all over. We're through with that. What you have left is to finish up assignment 4, which is due soon. It's due April 8th, and the final exam. So that's all that's left in this course. These marks, these percentages marks, are just as valuable as the ones early on in the course, right? The 5% for assignment 4 is the same as the 5% for assignment 1. But somehow now that the rest of your mark has been determined, it feels a little bit more urgent for a lot of people. Assignment 4 is long-ish if you don't understand what you're doing. It's not something you'll be able to leave until the last minute. So at the very least, I understand that everyone procrastinates. I did the same thing as a student. At the very least, go through the assignment and make sure there's no terms that you completely don't understand. Because the evening before and the day of is not going to be sufficient for this assignment. All right, so last time we were talking about these partial orders and graphical representations of those partial orders. So we came up with these things called Hasse diagrams, and they were a very nice way of describing a partial order because they were so succinct, right? They described a lot of information in a very simple way, and the thing that let us do that was knowledge of the fact that all partial orders are reflexive, antisymmetric, intransitive. So transitivity in particular saved us a lot of drawing in those diagrams. I'm going to show you one application of these diagrams today. And then we're going to move on to the last topic in the course, which is graphs, which is really the general version of these types of drawings. So you can draw lots of things other than Hasse diagrams, as you might have guessed. So the first thing I want to talk about today is topological sorting. So it's kind of a funny name. It's not obvious why it's called that. But it's motivated by a hopefully somewhat familiar setting. So we know that when we have these partial orders, you can't always compare everything in the partial order. Right? That's the point of a partial order. Every pair of elements might not be comparable. That's what a pair of incomparable elements is. So when you have these partial orders, it doesn't define a total order. So remember, a total order is an order where every pair of elements is comparable. And we like total orders because we can write them down. Right? If I write down a bunch of things in some order, that's a total order. The first thing comes before the second, which comes before the third, and so on. With a partial order, we don't have that, but sometimes we'd kind of like to. So here's an example. So suppose you're building a house. The steps required to build a house you can view as a partially ordered set. Because when you're building a house, you have to do some things before you can do other things. Right? That's not too much of a leap. So for example, you need to put up the walls before you can paint the walls. That definitely has to happen in that order. So you can define a partial order based on the must be done before relation. So let's see what that might look like. This is going to slightly oversimplify what it takes to make a house. So the very first thing that you have to do, the minimal element in this Hasse diagram, is make the foundation, let's say. And then after you've made the foundation, maybe the next thing you need to do is do the framing. And then after you do the framing, maybe you do the roofing. And these so far are kind of a total order. They have to happen in this order. You can't do the roofing before you've done the foundation. That doesn't make any sense. After that, maybe you want to do the exterior siding. But now you have some choices. right? You need to do the plumbing at some point. But you could also do the wiring now, and that would be okay, because somehow the plumbing and the wiring are separate tasks. And at some point you'll also need to do the exterior painting, but you can do that regardless of when you do the plumbing and the wiring. After you do the exterior painting, maybe you do the exterior fixtures. And this is somehow unrelated to the wiring and the plumbing. After you do the plumbing, you can do the flooring. After you do the flooring, you can do, say, the carpeting. After you do the wiring, after you do the wiring, you can do, say, the drywall. After you do the drywall, you can do the interior painting. Of course, it doesn't really make sense to do the drywall until the plumbing's done, and it doesn't really make sense to do the interior painting until the floor is done, so you have some requirements there as well. After you do the interior painting, you can do the interior fixtures. And somehow, when all of these things are done, you're done. So that needs to happen, that needs to happen, and that needs to happen. So this is an oversimplification of how you might build a house. But this is the partial order for the relation must be done before. All right, if you don't understand how a house is built, I mean, I certainly don't know all the details, but this seems reasonable, right? Okay, so this is a partial order, and I know it's partial because some things are not comparable. For example, plumbing and exterior painting are not comparable. There's no all upwards path from plumbing to exterior painting, and there's no all upwards path from exterior painting to plumbing. You can do those things in either order. It doesn't really matter. So this doesn't specify a total ordering, but it might be nice to have a total ordering, but we can't, right? We can't just throw a total ordering on here and hope that it works. But what you can do is you can define a total order that respects this partial order. So we're going to add in some comparisons that don't actually exist, but it's okay because we never violate comparisons that do exist. This is a little bit like taking the closure of a relation, except instead of having some property that we didn't have before, we're making the relation, the partial order relation, a total order. So this is a partial order. That must be respected. But it doesn't specify an actual ordering, a total ordering. So imagine if somehow you were building a house all by yourself. I mean, that'd be a lot of work. But in that case, you'd only be one person. So you can only do one thing at a time, and you need to do all of these steps. So you have to do them in some order, and the order that you do them in has to satisfy this. So all we're doing is taking this partial order and converting it into a total order that doesn't violate any of these rules. So I want to list all of these things, all of the elements of this partially ordered set, in some total order that respects the partial order. Is it clear what I'd like to do? So for example, foundation has to be the first thing. Framing has to be the second thing. Roofing has to be the third thing. Exterior siding has to be the fourth thing. But then I have some choices, right? I could do plumbing, wiring, exterior painting. Those would be a fine order. Or I could do wiring, exterior painting, plumbing, or whatever. So this isn't going to be unique, right? There's going to be more than one possible answer here, for sure, unless the original thing really is a total order. So we'd like to specify a valid total ordering. So we might want a valid total ordering. And here valid means it respects this partial order. All right, so to phrase this formally, for those who like formal definitions, a total ordering, which I'll denote like that, is compatible with a partial ordering, I'll call it R, if we have A is before B in the total order whenever A is before B in the partial order. So that's what it means to respect the partial order. Is it clear what I'm trying to do? All right. So we need one observation that'll let us do this. And this is the observation. The observation is that every finite, non-empty post set has at least one minimal element. Every finite, non-empty post set has at least one minimal element. Does that seem like something that's reasonable? Does anyone see why this might be the case? I'm not going to do a full proof, but intuitively, does anyone see why? Yeah, it's somehow the start point. If you draw a diagram, the Hasse diagram for a post set, all post sets have Hasse diagrams, something has to be at the bottom, right? If there's something there, and there is something because it's non-empty, something has to be at the bottom. That's the easy way of seeing it. So that's not a proof, but that's the intuition behind the proof. Okay, so using this operation, this observation, I'm going to try to find a compatible total ordering. So how might I use this observation to do that? What has to come first in my total order? Yeah, the minimal element, or one of the minimal elements, has to come first. So what do I do after that? What happens next?
Remove that element.
Yeah, I remove that element, and what am I left with? Right, a brand new Hasse diagram, and that Hasse diagram is a partial order, so it has a minimal element, so I can take it out. And once I've removed that, I'm left with another Hasse diagram that must have a minimal element, so I take it out, and so on. And I keep doing this over and over and over again until I'm out of elements, and at that point, I'm done. That's all there is to it. So the idea is to remove a minimal element and place it at the end of the current total order, and now repeat. And doing this is called topological sorting. There are other ways of achieving this, but this is the simplest one I know, so that's why I'm explaining it here. So this is called topological sorting. So we're sorting this set with respect to a partial order, as opposed to a total order, which is how we're used to sorting sets. So I'm going to do this on a smaller example than the previous one, and then I'll show you how to do it on the previous one later. So for example, let's say we have the divides relation on the set 1, 2, 3, 4, 6, 8, 12. Right, this is the one we had last time, I think. It looks like this. I have 1 at the bottom, going up to 2 and 3. That goes to 4, 4 goes to 8, and above the 3, I have a 6, and I have a 12, and there's connections like that. This is my, oh, this thing at the bottom is 1, I should say. That's my Hasse diagram for the divides relation on 1, 2, 3, 4, 6, 8, 12. And what I'd like to do is topologically sort this thing. So I look for the minimal element, or one minimal element. In this particular case, there's only one minimal element. It's 1. So I add 1 to the end of what I have so far. I don't have anything so far, so I just put down 1. And now what I do is I remove 1 from my Hasse diagram. So I take out 1. And in taking out 1, I also need to take out everything leaving 1, right? Because every one of these edges has to start somewhere and end somewhere. So I do that, and now I'm left with a new Hasse diagram. Right? It looks like this. So what are the minimal elements in this Hasse diagram? 2 and 3. So at this point, I can take either one of them, right? You can take any minimal element you like. So let's take 3. So now I have 3, so I remove 3 and everything leaving 3. All the edges leaving 3. And now I'm left with a new Hasse diagram. What are the minimal elements of this Hasse diagram? Just 2. Right now there's not a choice. 2 is the only minimal element. So I put 2 next in my order. And now I remove 2, and I'm left with this. So what are the minimal elements in this Hasse diagram? 4 and 6, so let's take 4. So I remove 4, and I'm left with this. What are the minimal elements in this Hasse diagram? Yeah, 6 and 8. 8 does count as a minimal element. It counts because there's nothing leaving it in the upwards direction, right? That's what it means to be minimal. So we could take either one. I'm going to take 8. So I remove 8 and everything leaving it. In this case, there's nothing leaving it. So now I have another Hasse diagram, 6 and 12. 6 is the minimal element, so I put 6. I remove 6. 12 is the only thing that's left, therefore it's minimal. So I have 12, remove 12, and now I have nothing left. But I do have all of the elements in the set in this order. So this thing here is a valid total order of the poset. So this thing is the result of topologically sorting that set. And this seems kind of weird because normally we wouldn't consider this thing to be sorted, right? This thing sorted would be 1, 2, 3, 4, 6, 8, 12. That sorting is with respect to the less than relation. Well, the less than or equal relation. But we're not sorting with respect to that relation, we're sorting with respect to the divides relation. Yeah?
Why do you remove 8, 3, 4, 6?
So I don't care about the numerical values of these things. All I care about is the divides part. Notice that 6 and 8 aren't comparable elements with respect to the divides relation. Neither divides the other. So it doesn't matter which order they appear in. I could have done it in the other order. That's fine. I'm doing it in this order so you see that it doesn't matter that it's bigger. Yeah?
Is that the same reason for why after you move 2, you put 4 instead of 6?
Why after I move 2, I put 4 instead of 6.
Like if 6 comes directly after 2.
So in that element, in that diagram, it looked like this, right? At that point. So at this point, the minimal elements are 4 and 6. I could have removed either one. So if I removed 4, I could have done 6 instead. That would have been fine. It would have appeared earlier. So there's more than one right answer to these, and that's okay. Other questions? Okay, so this thing doesn't seem sorted. Why is it sorted? What property does this thing have? So let's look at 4 here, for example. Why is 4 in the correct position? Yeah? Everything that divides 4 is before it. Yeah, so what divides 4? 1 divides 4, 2 divides 4. And they're both to the left of 4. Everything to the right of 4 does not, right? 8 doesn't divide 4, 6 doesn't divide 4, 12 doesn't divide 4. All right? That is exactly the property we were looking for, right? That's what we wanted. We wanted it to respect the partial order. We could do the same thing for 6. What divides 6? 1, 3, 2. Those all appear before 6. Some other stuff that doesn't divide 6 also appears before 6, but this is unavoidable because divides is not a total order, right? It's a partial order. Yeah? Right, so that's okay. 8 is before 6, but 8 doesn't divide 6. So the stuff before can or cannot, but the stuff after definitely does not. Other questions? Yeah. If you change so no matter how you order them, if you do this proper topological sorting with the Hasse diagram, it will always have this property. If it doesn't, you've made a mistake somewhere. Okay, any other questions about this? Yeah?
So for these, you could say that everything that does divide it is definitely to the left, but not everything that does not divide it is.
Not everything that does not divide.
For example, 3 doesn't divide 8 to the left of it.
Yeah, that's okay. There'll be extra stuff there, and there has to be, because there are these elements that are incomparable, and they have to go somewhere, right? Either to the left or to the right. Other questions? Okay, so let's do this other one just verbally. What would the first thing be? Foundation, so maybe I'll number them. Then framing, roofing, exterior siding. What could happen next? Plumbing, sure. What could happen next? Flooring. What could happen next? Yeah, carpeting's fine. What could happen next? Let's say, I don't know, exterior painting, then exterior fixtures, and then wiring, drywall, painting, interior fixtures, and then we're done at 14. There's lots of other ways that you could do this. If you don't want to go scratching things out every time you go through this topological sorting, you can color them in or shade them or cross them out or something. And then you can add the thing on top once everything underneath it is crossed out. That's really doing the same thing. Yep.
Could you have gone like after exterior siding, plumbing, then wiring,
After exterior siding, plumbing, wiring, exterior painting, yeah, that would be totally fine too. Yeah. Other questions? Okay, so it wouldn't be unreasonable on a final exam, for example, to be given a partially ordered set, perhaps as a Hasse diagram or perhaps as a description, and ask you to compute a valid total ordering. That would be something that's pretty recent. All right, so we're ready to start talking about the very last topic in this course, which is something I'm sure many of you are happy to hear. The last topic is a big one, though, and it's graphs, and it's what we're going to be spending time on until the end of the course. So this is lecture 21. We have 25 lectures. 21 through 24 will be graphs, and then the last lecture will be a big review lecture so that we're all prepared for the final exam, hopefully. All right. So graphs are really useful tools because they can be used to model problems from virtually any field. It's a very general technique. So we'll define what a graph is. A graph is a pair of sets V, comma, E. V is called the vertex set. E is called the edge set. It's a little messy. Edge. Okay. Each edge in E describes how vertices in V are connected. So these vertices are connected in various ways, and the edge set describes what those connections look like. So I'll give you an example. So maybe I have a graph that looks like this. The black circles are the vertices, and the black lines are edges. So this is a perfectly good graph. Oftentimes, we give names or labels to the vertices. So maybe this vertex here is San Francisco. This vertex down here is Los Angeles. This vertex here might be Denver. This vertex here might be Chicago. And we might have Detroit, New York, and Washington, for example. So this is a graph, and maybe this graph represents direct flights between cities, or something like that. Okay. It could also represent freeways between cities, or railroads between cities, or maybe phone lines between cities, or fiber optic cable between cities, or things like this. So lots of different things can be modeled using graphs. Anytime you're in a situation where different things are connected to other things in some pattern, which it's not too hard to believe happens very frequently, you might want to consider modeling your problem as a graph. And the reason you would want to do this is because the idea of the abstraction of being a graph is something that's very common, so mathematicians have spent a long time working on it. So by modeling your problem as a graph, you get all the benefit of hundreds of years of mathematicians' efforts to prove things about graphs or come up with algorithms that work on graphs. That's the real benefit of modeling problems in this way. So as mathematicians, we love to classify things. So this graph has a particular classification. This is a simple graph. And the reason it's a simple graph is really two reasons. The first reason is that no edge connects a vertex to itself. Right? So I'd never have a situation that looks like this. That's not allowed in a simple graph. Other types of graphs it is allowed, and I'll say some of the different types of graphs soon. So this is a simple graph because that's not allowed, and because there's only one edge between two vertices. So I never have a situation like this. A different type of graph handles that, but that graph isn't called simple. This seems like a good time to bring this up. The plural of vertex is vertices. So if you have more than one vertex, you have some number of vertices. Something that happens a lot is students will then go back to the singular and say vertice. Don't do that. The singular of vertices is vertex. Okay, so that's great. In this particular graph, edges don't have directions. So you could, let's say these were railroads, you could take the train from San Francisco to Denver, and you could also take the train back. All right? So that's a special situation because sometimes it is nice to have directions. So for now, let's concentrate on the case when we don't have directions. So this graph, maybe I should say in this graph, edges don't have a direction. That's not required. When edges don't have a direction, we say that the graph is undirected. That's the term we use for that. Because the graph is undirected, to define an edge, you really just need the names of two vertices in any order, and that defines the edge. So in an undirected graph, edges can be represented as sets consisting of two vertices. All right, and those vertices are the vertices on either edge, or either end of the edge. So if I wanted to be completely descriptive about this graph, I could. The vertex set, maybe I'll copy this just for, oh no, it's probably fine. So if I copy this graph, and I want to write some kind of representation for this graph, which is something we're going to be concerned about because this graph needs to get stored somewhere if we're going to use it. Remember, a graph is a pair of sets, V and E. So I have to say what V is. Well, the best way I know how to identify these vertices is by their label. So V might be the set San Francisco, Los Angeles, Denver, Chicago, Detroit, New York, and Washington. Oops. And then the edge set, well, to specify an edge, we need to specify both endpoints, or both vertices that are on that edge. And we can do that, because direction doesn't matter, by specifying them as sets. And we sort of want to be able to do that, because going from Denver to Chicago is the same as going from Chicago to Denver. You use exactly the same edge. So we'd have something like San Francisco, Denver, San Francisco, Los Angeles. So we've done San Francisco, Denver, San Francisco, Los Angeles, Los Angeles, Denver, Denver, Chicago, Chicago, Detroit, Chicago, Washington, Chicago, New York, Detroit, New York, and New York, Washington. Okay? So that would be a very explicit representation of this graph, right? And hopefully you believe that it's tedious to do this all the time. And there are better ways of representing graphs that I'll talk about soon. Okay, but this is the full official mathematical definition of this graph. So any questions so far? Yeah?
Wait, what did you say that the graph is non-directional?
We say that it's undirected. Undirected. Yeah.
In a simple graph, what would be, can I have
Right, so simple graphs can be directed or undirected. So we would say this is an undirected simple graph. I'll get into the full sort of terminology soon. Other questions? Yeah?
Could I understand how you decide order in a pair?
No, it doesn't matter because sets don't have an order, so I could have easily written it the other way and it would be exactly the same. So relations, so something like a partial order causes an order based on what's in the relation, and each thing in the relation is an ordered pair, yes. But the relation itself is a set, so the order you write down those pairs doesn't matter, it's just the pairs that do. Yeah? So could you have something like, if there's some other city here, like, I don't know, Austin? Yeah, that's completely fine. Other questions? All right, so sometimes you do want to allow multiple edges between vertices. That does happen. That's just fine. What you get when you have that situation is called a multigraph. So you know you have a multigraph when there's possibly more than one edge between vertices. So this would be an example of a multigraph. Something like that. So notice between this vertex here and that vertex there are in fact 3 edges. Might seem weird that you would ever want to do that. You could use this to model redundancy. So for example, between 2 cities there might be more than one highway, and that makes sense because if there's some horrible accident on one highway, you probably still want to be able to get there through some other route. The same is true of things like phone lines or other telecommunication lines, right? If one of them gets cut or destroyed or fails for whatever reason, you still want to be able to make phone calls to that city. So this model is redundancy. So notice here that edges are still undirected. So you can represent them as sets of 2 vertices. But how would this fit into our V equals something, E equals something situation now? So how would I write down the set representation of this graph? Yeah?
You like, I don't know, they're not labeled, but like for each of the edges, just cover them or something?
Yeah, so there's a couple of things I could do. So let's say these vertices are A, B. You want to have some kind of repetition in there, but you can't because it's a set. So you need to add something else. One thing you could do is, as you said, you could label these edges 1, 2, 3. That would be a perfectly good solution, and in fact, some applications do exactly that. The alternative would be to record the multiplicity of the edge. So the multiplicity of this edge between A and B is 3, because there's 3 edges between A and B. So what you could do is you could store it as the set A, B, 3. And that way you don't need to label the individual edges, you just need to count the edges that are there. This assumes that your labels then aren't integers that would somehow get mixed up with what's going on. Which one you should do depends on whether or not you need to talk about the edges individually. Right? If I only care that there's 3 routes from here to Toronto, then I just need the multiplicity. If I care about the name of each highway, then I would want to label the edges. Those are the 2 alternatives. So edges now appear more than once. So we need some way of representing that. The number of times that they appear is the multiplicity of the edge. So if there's 3 edges between A and B, it has multiplicity m. So if there are m distinct edges, between vertices A and B. Then the edge AB has multiplicity 3. Or sorry, multiplicity M. In my example, it's 3, but in general, it could be however much you like. And these multigraphs are used to model things like redundant connections in a network. So that takes care of one restriction. So we said the first graph I did was a simple graph because it didn't have multiple edges between vertices, so it had every edge had multiplicity 1, if you like, or there's not an edge. The other restriction I had was that there were no edges that go from a vertex back to that same vertex. But sometimes you might want to have that, and graphs do allow you to do that if you want, but again, it has a special name. So we might want to relax the restriction that there are no edges from a vertex to itself. You can. So those edges are called self-loops. And graphs that have self-loops are called pseudographs. So if you have a self-loop, you are a pseudograph. These come in handy for things like loopbacks in networks. So there's always, so if you're on a network, there's always an IP address that refers back to yourself. And that's useful for various applications that I won't get into now, but they do come in handy. So everything I've talked about so far has an analogous version where the edges are directed. Right? So you might sometimes want to enforce directed edges. This comes up, for example, if you had a road network and you had one-way roads, then that might be something that was useful. Right? You can only get from this corner to that corner going north or something like that. So we can also have directed versions of these graphs. So I'll give you an example of what that looks like. Let's say I wanted to have a directed multigraph. So I could have something like this. That goes there. This goes there. That goes there. Maybe there's another edge in this direction and another edge in the other direction. Goes over there. Something like that. Would be a directed multigraph. Does that make sense? Yeah? So you could draw the arrow in, but of course it doesn't have a particular meaning because you can always get for you can always follow that edge somehow. All right, so this is somewhat complicated because I've given you a lot of different types of graphs. So I'm going to summarize them in a hopefully simple table for you. So what's in this table? The name of the graph, the type of the edge, so either directed or undirected, whether or not you're allowed to have multiple edges, and by that I mean multiplicity bigger than 1, and whether or not you're allowed to have self-loops. Okay, so the first type of graph we talked about was a simple graph. The edges were undirected, we were not allowed to have multiple edges, and we were not allowed to have self-loops. That's the very first one we saw. The next type is a multigraph. In this case, again, the edges were undirected. You were allowed to have multiple edges, but you're not allowed to have self-loops. The next type is a pseudograph. A pseudograph is, again, undirected. You are allowed to have multiple edges in a pseudograph. I didn't say that, but typically you are assumed to. And you are indeed allowed to have self-loops. And then you have these same things in the directed sense. So you could have a simple directed graph, and in this case the edges would be directed. You would not be allowed to have multiple edges, and you would not be allowed to have self-loops. Okay? One important distinction, though, is in a simple directed graph, the direction of the edge matters. So the edge from A to B is not the same as the edge from B to A. So you could have both of those, and you wouldn't really be a multigraph. Going a bit further, you have a directed multigraph. In that case, again, the edges are directed. You are allowed multiple edges. And for reasons that escape me, typically we don't make the distinction between pseudographs when they're directed. This is likely because it doesn't matter which direction you follow the self-loop in. So I'll say for this course, directed multigraphs are allowed to have self-loops. We won't talk about a third thing, a directed pseudograph. Is that okay? So it's important to be comfortable with these names. If you see multi, that refers to multiplicity. If you see pseudo, that refers to self-loops. And you just make the distinction on whether it's directed or undirected. So usually the names of these things are fairly descriptive once you're used to working with them. So there's lots of different graphs. And there's many uses of graphs. This is something I alluded to at the beginning. The first one, which, because it's 2015, I'm obligated to say, is social networks. So if you think about your favorite social network, so Google+, Facebook. So Facebook is a graph, right? It makes up a graph. The vertices are all people. And there's an edge between two people if they're friends on Facebook. So this is a certain type of graph. Which type of graph would this be? Yeah? So why would you say a multi-graph? Okay, so we don't have self-loops for sure. Right, so that means it'll be undirected.
Yeah.
Okay, so it will be undirected, so it'll be one of these three, and we don't allow self-loops, so in fact it'll be one of these two. So the distinction is, will it be a simple graph or a multi-graph? Yeah. So I would say probably a simple graph, and the reason is I can't be friends with someone twice. There's only one connection between me and another person. So Facebook would be an example of a simple graph. So if you come up with a really nice simple graph, it could be worth billions and billions of dollars apparently. Okay, so that's one. There's also the Hollywood graph. So this is the graph where all of the vertices are actors, so people who have been in movies. And there is an edge between two actors if they've ever acted in the same movie together. All right, so what kind of graph would that be? Yeah? Yeah, so you could model it as a simple graph if you didn't care which movie they were in. But if you wanted to be able to say what the movies were, then maybe it would be nice to have it as a multi-graph. because two actors can be in more than one movie together. So maybe your graph wants to model that. So this would be an undirected graph for sure. Self-loops you wouldn't really have. And it would either be simple or a simple graph or a multi-graph. You could make a strong case for both. It depends on what you wanted to do with it. And the 6 degrees of Kevin Bacon thing, well, that's really asking a question on this graph. So is there a path from any actor to Kevin Bacon of length at most 6? That's what the game is. Right? And I'll tell you what a path is later. I'll describe it more fully. But a path is basically a sequence of vertices that are all connected to the next one in the sequence. That's what a path is. So that's another graph. There's another graph called the collaboration graph. So this is something that gets brought up in academia. So as academics, we sit around in our offices all day when we're not teaching, and we come up with hopefully neat ideas, and we publish papers on them. But typically, we're not that smart, and we need help. So we get together with other academics, and we write papers. And this particular graph is the graph of collaboration. So there's a vertex for every professor, and there's an edge between two professors if they've ever published a paper together. So this is basically exactly the same as the Hollywood graph, except it's for nerds, I guess. We play a similar game to the Kevin Bacon game. So there's a very famous mathematician named Paul Erdős, and he was very, very prolific and wrote many, many papers with many, many people. And we measure how cool we are based on the number of connections we have with Paul Erdős. So that's a fun game we play. I think my number's like 2 or 3 or something. Not to brag. All right. Another type of graph is a call graph. There's a few types of graphs which you might want to consider call graphs. So one would be is if you're writing a program, and you know how you have the situation where you're in a function, and that function calls another function, which calls another function, and so on. Well, that's a graph, and that's handy to have because it gives you an idea of what's going on in your program. So what kind of graph would that call graph be?
Probably a direct computer graph, because functions don't typically call, like, one function calling the other is not the same as the other function calling the first. The function can call itself.
Yeah, exactly. So I would say that it is a directed pseudograph or directed multigraph if we assume that multigraphs allow self-loops. Because certainly a function can call itself, that's what recursion is. And if you're analyzing the program, it probably matters which function called which. But again, you can massage this a little bit depending on what your particular applications are. Another thing that might be considered a call graph would be if you're working on some kind of telecommunications network. And in that case, there's a vertex for every phone in your system. And there's an edge between two vertices if there's an active call between them. So maybe you could further extend this to cellular activity or something like that. That's kind of a neat graph because now that graph is changing a lot over time. The other ones were too, but somehow it seems like this graph changes very, very frequently as calls connect and disconnect as time moves on. So that's another call graph. Another kind of famous one would be a web graph. So this is the graph where every vertex is a web page, and there's an edge between two vertices. If there's, so let's say vertex A to vertex B, there's an edge there if there's a hyperlink on page A that leads to page B. That's what the web graph is. That used to be much easier to define before we had all sorts of weird JavaScripting happening. But yeah, that's a perfectly good graph as well. So any questions about these graphs? I don't care so much that you memorize these graphs. My point is that it's not too hard to believe the graphs are very useful, right? They're used to model a lot of different problems. And if we can cast our problem as a graph, that's good because now we have this abstract setting to work on our problem, and lots of people have worked really hard to solve problems about graphs. So if you can take your problem, convert it to one about graphs, then you get the benefit of a lot of really, really smart people working on these problems for a really long time. That's why we want to do this. All right, so let's talk a little bit about representing graphs. We already saw kind of a bad way, right? We already saw a bad way, and that was listing all of the vertices in a set and listing all the edges in a set. And that wasn't so good because, well, first of all, it was a pain, it was a lot of writing. And second of all, if you wanted to ask a question about that, about the graph, so let's say, hey, is vertex A connected to vertex B? That representation isn't great. It doesn't do anything for you, right? If you wanted, so let's go up to what I wrote for this graph. If I wanted to know, is Denver connected to Chicago? Well, the computer doesn't have this nice diagram on the right, on the left. What the computer has is this, or some representation of that. So if you wanted to check to see, is Denver connected to Chicago, you have to go through here one by one until you get here, and then you say, oh, it is, great. Right? That's not a very fast operation. If you think of this in terms of analyzing the algorithm, it takes about linear time to figure out that those two things are connected. And this is precisely the idea behind data structuring problems. And this is something I do a lot of, because that's what my research area was. Whenever you have data like this, you want to structure it in a way that it is useful based on the kinds of questions you're going to ask. So if you're constantly asking, hey, is this vertex next to the next one? Next to this other one? Well, then this representation is really bad because the operation you care about takes a really long time to do. So it would be nice if we could represent this data in some other way. So I'll show you two other ways you can do this, and in fact there's lots and lots of ways to represent graphs. All right, so here's one, and this is the adjacency list. All right, so the way an adjacency list works is for every vertex in your graph, you list the vertices that are connected to that vertex by an edge. That's it. For each vertex, list the vertices that are connected to it by an edge. So those vertices that are connected to a vertex by an edge, we call those vertices adjacent to the initial vertex, beside the initial vertex. So such vertices are said to be adjacent. So that's something I'll use all the time. This particular technique, as we'll see, happens to work for both directed and undirected graphs, even if they contain self-loops, which is kind of nice. So I'll do an example here. Let's say we have vertex A, B, C, D, and E, and it looks like this. Oops. So this is my graph, and notice that this is a simple undirected graph. So I'd like to make an adjacency list for this thing. So what I do is I list each vertex, right, because it says for each vertex. So I'll say vertex A, B, C, D, and E. And now for each one, I'll list the vertices that are beside it. So beside, maybe I'll draw this line a little bit better. Beside vertex A is vertices B, C, and E. B, C, E. That's kind of nice. What's beside vertex B? Just A. What's beside vertex C? A, E, and D. What's beside vertex D? C and E. And beside vertex E, A, C, and D. So this is the adjacency list for this thing. And this is a better, better way of structuring your data sometimes. So now if I want to see is vertex C next to vertex A, I go to A's list, and I only need to look at the ones that are adjacent. So I need to check all of the ones that are adjacent to A, rather than the old way, which is I need to look at every edge in the entire graph. So this isn't a huge improvement. I mean, it is sometimes, but in the worst case, it's maybe not that great. Right? I could have a vertex that's in the middle that's connected to everything else, and in that case, it's not really much of a savings. But sometimes it is, so this is better, but not perfect. But this is really nice if I, say, wanted to get all of the vertices adjacent to the vertex. So let's say the question I wanted to ask a lot was not, is A next to B, but list all of the things next to A. Well, then this is a great representation because I have the answer stored right there. Yeah?
Can it still be a graph if you have a vertex with no edges on it?
Yeah, that's completely fine. So a vertex might not have any edges going out of it. That's fine. Other questions? Yeah?
Yeah, kind of what that guy said. Is it still part of the graph? Like if you do a vertex right there that wasn't connected?
Yeah, so if I had like F here,
Yeah.
yeah, so that's still part of the graph, and I would have an entry for F, and there would be nothing there. So maybe you would just say none. And that's completely fine. That's fine in a graph. This would be like a person on Facebook who has no friends. They're still part of Facebook, they're just not friends with anyone. All right, so as I said, we can use adjacency lists even in the case of, say, a directed graph with self-loops. That's completely fine. So let's make a slightly fancier graph. So let's say I have edges there, 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 going back like that, and like that. So this is a bit more interesting, and I'll label it the same as I did before. We can also have an adjacency list for this thing. So my vertices are A, B, C, D, and E. What is next to A, where next means you have to follow the arrow in that direction? So if I follow the arrow from A, I can get to B, D, and E. Right? I leave vertex A and go somewhere else. I'm not entering vertex A. Okay, so if I go to B, I can get to C, and I can also get back to B. So B and C are the vertices I can go to. What about from C? What can I get to from C? Any ideas? Just D. What about D? Just C. And what about E? It can get to itself and D. That's all fine. Again, a situation might happen where you can't leave. So maybe I have a vertex F up here, and I can get there from A, but once I'm there, I can't leave. Even though there's an edge on F, it's not pointing in the right direction. So in this case, nothing is adjacent to F. Does that make sense? So this is an adjacency list. There's another way of representing graphs. It's slightly different. And this way, which is method 2, is called an adjacency matrix. So the way an adjacency matrix works is you have one row and one column for each vertex. So suppose we have vertices, I'll call them V1, V2, V3, all the way up to Vn. Well, then you have one row and one column for each vertex. and the entry at row I, column J, is 1 if that corresponding edge is part of the graph, and it's 0 otherwise. Zero otherwise. So if this is going to work, it means you need to fix some ordering on your vertices. You need to give them numerical labels. Yeah?
So that's a adjacent matrix?
Adjacency matrix. So let's do an example. Let's say I have A, B, C, D, connected like this. And notice this is a simple undirected graph. Then what I do is I fix some ordering on my vertices. So I'll always have them in the order A, B, C, D. Right? That's the easiest one, is going alphabetically. So I make a matrix with 4 rows and 4 columns. And it's 4 rows and 4 columns because there's 4 vertices. So I'll have rows for A, B, C, and D, and columns for A, B, C, and D. And the critical thing is that you go in the same order for both of those, right? That's important. And once you have that, you just fill this thing out. So A is my first row, and I look at what A is connected to. A is connected to B, C, and D. So A is connected to B, C, and D, but it's not connected to A. So I have a 0 there. Now I go to my next row, which is row B. B is connected to A and C. So B is connected to A and C, but not B and not D. Now I go to the next row, which is row C. What is C connected to? It's connected to A and B. So A and B, but not C and not D. And finally, D is connected to A, but nothing else. So 1, 0, 0, 0. And this is the adjacency matrix for that graph. Yeah? Yes, that's exactly what you would do. Instead of so if there were 2 edges from A to B, you would have a 2 right here instead of a 1. And I'll do an example like that in a second. Does anyone notice anything about this matrix? Okay, something more general maybe, yeah? All the pivots are zeros. Okay, so that's because no self loops are allowed. So the main diagonal will be all zeros. Other properties, yeah?
If it's one directional, you only have to do like 1 point.
Yeah, if this thing is undirected, then this matrix is symmetric. It's symmetric about the main diagonal. So that means if I look here, this is the main diagonal, and I know that's all zeros because there's no self loops. But now if I reflect about this main diagonal, everything's the same. So I have a 1 here, a 1 there. A 1 here, and a 1 here. A 1 here, and a 1 there. A 1 there, and a 1 there. 0 there, 0 there, 0 there, and 0 there. So if you took this matrix and flipped it like you were folding a napkin or something, all of the entries would line up. And that's because the edge from A to B is the same as the edge from B to A. That's because this is an undirected graph. The exact same thing works for directed graphs, but in that case it won't be symmetric. So you can do this. So I'll first state those properties. So 2 properties when the graph is simple. So the first property is that it's symmetric. And the reason it's symmetric is because edge from A to B, if and only if edge from B to A. And the second property is that the main diagonal is all zeros, and that's because there are no self-loops. So that's not required. You can do this exact same thing for multigraphs. So if you want to support multigraphs, so as an example, I'll even say directed multigraph. So let's say I have A, B, C, D, and I have an edge here, here, let's say there, 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 and there, say. And this is A, B, C, D. So now what I'll do is I'll make a matrix just like I did before. I'll keep it in the same order, so A, B, C, D, A, B, C, D. And now I just write down the multiplicities instead of 0 or 1. And notice now I also have directions, which means I'll need to do a little bit more work. So, what can I get to from A? I can get to B, and I can get to C. So I can get to B, and I can get to C. But I can get to B two ways. I can take this edge here, or I can take that edge there. So this 1 is really a 2. And I can't get back to A, and I can't get to D. All right. What about B? Well, I can get to C, and that's it. And there's only one way to get to C. So I have this. What about C? Well, I can get back to A, and there's only one way to do it. And I can get to D. So I have A and D, but nothing else. And what about D? Well, from D, I can only get back to D. That's the only thing I can do. So notice now, we no longer have the property of symmetry. And we don't have symmetry because this graph is now directed. So just because we have an edge from A to B doesn't necessarily mean we'll have an edge from B to A. And we also lose the other property, which is the main diagonal, that the main diagonal is all zeros, because now we allow self-loops. So this is self-loop from D back to D. Any questions about this? Yeah? Yeah, so you could do that. At that point, it becomes sort of difficult to support both multiple edges and edge weights. You need something else. But yes, you could also do that in that case. All right, so notice that adjacency matrices are good in a different situation. So the original thing I said was, what if I want to check to see if A is next to B? An adjacency matrix can answer that question really, really quickly, right? Because this thing here is really just an array, and the big benefit of using arrays is that we can index into them in constant time. So if I want to know is A next to B, I know I go right here, and my answer is whatever is there. So that's really great. That's better than an adjacency list, because in an adjacency list, I would need to possibly go through the list of things adjacent to A, and that can take some time, right? Because I might have to go through all 10 things, but nothing's there. In a matrix representation, I can figure it out immediately, and that's really nice. But if I go back to an adjacency list and I said, okay, well, another thing I might want to ask is list all of the things that are adjacent to A. How would I do that in an adjacency matrix? Yeah, you have to go across the entire row. How many things are in the row? N, right? As many things as there are vertices. So in an adjacency matrix, it's very time-consuming to list all of the things that are adjacent, but it's very fast to determine if any single thing is adjacent. There's also another big drawback to using an adjacency matrix. Does anyone see what that drawback is? It has nothing to do with time. Memory space. So an adjacency matrix needs to store a bit, basically. So if we assume it's just for a simple graph, it stores a bit for every single vertex-vertex combination. And if there's n vertices, that means your matrix has size n squared. Now, if it is undirected, you can cut that down a little bit because it's symmetric and you know it's symmetric, but that's still just n squared divided by 2, roughly. It's actually a little bit less because you don't need the main diagonal either. That's still not great. That's still theta of n squared. So you need quadratic space to store these things. Now there are some slightly clever tricks you can do with something called hashing to bring this down a little bit further, because as it turns out, you don't really need to store the zeros. You really only have to store the ones. And if there's a lot of ones, then your storage will be big, but somehow that's okay because there's a lot of edges. And if there's a lot of edges, you can't really avoid storing them. If we go back to the adjacency list representation, what's the storage required by this thing? Yeah?
Well, I guess 2 references per line.
2 references per line.
Because A is connected to B. That means that A needs to store B and B needs to store A.
Right, yeah. So let's look at it this way. How many lists do I have? N lists. How many things could be in a single list? N at maximum. So in the worst case, it seems like this is going to maybe take quadratic space. Maybe. What's one thing that sort of saves us a little bit, though? Every element almost certainly won't be. And what if every element is connected to every other element? What happens then? It's no better, it's no worse. The key thing is that if every element is connected to every other element, somehow your graph is really, really big, right? There's a lot of edges in that graph. And it's not really fair to be able to expect that if you have a lot of things in your graph, that you wouldn't have to store a lot of things when you store the graph, right? In a graph, how many edges could there be? Well, every vertex could be connected to every other vertex. So in the undirected case, that's about n squared. It's theta of n squared connections. So if your graph is really that large, it's somehow not realistic to expect that you wouldn't have to do that. But the nice thing about the adjacency list representation is that space usage is only large when the graph is actually large. Whereas in the matrix representation, if you do it as I've described, the space usage is going to be large all the time, regardless of whether there's one edge or n squared edges. And that's the key difference. So it's important to pay attention to these things. If checking to see if something is adjacent to something else is really important, maybe it's worth it to you to spend that extra storage space, right? It's about trading off time for memory, which is a common theme in computer science. All right, so I'll stop here for today, and next time we'll pick up and learn more terminology about graphs.